KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Neet, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we start with the 15th problem. See here, first you see the problem, then we will go for solution. See here. So in this chapter, dual nature of light, it is 15th problem from numerical point of view, right? See here, light of frequency nu falls on a material of threshold frequency nu naught, right? Full stop. Maximum kinetic energy of emitted electron is proportional to, right? So in this problem, we have to understand nu is the frequency of incident light and nu naught is the threshold frequency. Nu naught is the threshold frequency, right? So threshold frequency means minimum frequency of incident light, right? Minimum frequency of incident light required for the emission of electron from a metallic surface. Okay, right? And here, this is what I told you already, is the frequency of incident light and it is the threshold frequency, and he is asking maximum kinetic energy of emitted electron is proportional to, okay, right? And you know that what is Einstein's photoelectric equation, right? So actually Einstein's photoelectric equation is E is equal to phi naught plus Ke maximum. E is equal to phi naught plus Ke maximum. E is the energy of the incident radiation or incident light, and phi naught is the work function, and Ke maximum is the maximum kinetic energy of photoelectron. Okay, right. Next, that same equation we are writing like this, right? So in place of E, we are writing H nu. Ke maximum is as it is plus phi naught. Okay, phi naught is the work function, and you know very well, phi naught is equal to H into nu naught. Phi naught is equal to H into nu naught. Do we know or not? Yes, because nu naught is the threshold frequency and H is the Planck's constant. Okay, right. The same thing, this equation, just in place of phi naught, we are going to write H nu naught. Then if you write Ke maximum as a subject, Ke maximum is equal to H into nu minus H nu naught. H nu minus H nu naught. Okay, right. And H is the Planck's constant, right? So when we are talking about dependency and independency of physical quantities, we don't bother about constants, because constant means its value is not changing. Its value is not changing with the time and place. Then it is called as constant. Okay. So here you can say that Ke maximum is directly proportional to nu minus nu naught. That is what difference in the frequency of incident light and threshold frequency. Ke maximum is directly proportional to nu minus nu naught. Okay, right. Next problem. Add the problem. Say here. In an experiment of photoelectric effect, the stopping potential was measured to be the stopping potential was measured to be V1 and V2 volts with the incident light of wavelength lambda and lambda by 2 respectively. The relation between V1 and V2 may be, right? What is photoelectric effect experiment? You know, that is what when a metallic surface is going to expose to the invisible form of energy, that is light, then emission of electrons takes place from a metallic surface. So which is the natural phenomena, and that is, you can also call it as a photoelectric effect, and you can also call it as experiment of photoelectric effect. Then stopping potential. So what is meant by stopping potential means, you know, when we are doing that photoelectric experiment, there is what cathode is there, anode is there. Otherwise you can instead of these two things, right, we can call it as, that is what, emitter plate and collector plate. Emitter plate and collector plate, right? So the invisible form of energy light is going to incident on emitter plate, right? And I am not sure that when light is going to incident on emitter plate, immediately electrons will come. I am not sure, because there should be some wavelength, and there should be some frequency, and there should be some energy, right? So that's why I am not going towards the factors how the photoelectric effect affects. As simple as such, in a simpler manner I am saying. So basic thing is, when the light of certain amount of energy or suitable amount of energy, right, with the proper frequency and with the proper required wavelength is going to incident, then emission of electrons takes place, right? So these electrons will travel towards the collector plate, okay, right? And you know, the potential of collector plate, if you want, you can vary, you can change. So at a particular instant of time, for a particular value of negative potential of collector plate, you know, no electron will reach collector plate. So all the electrons will send back to the emitter plate. So here itself you can say that, you know, the photoelectric current is 0. So the value of negative potential of collector plates, the value of negative potential of collector plate at which no photo electrons reach the collector plate, so the photo current is 0, is called as stopping potential, right? So whenever we are getting the term stopping potential, whenever we are getting the term threshold frequency, whenever you are getting the term threshold wavelength, whenever you are getting the term photoelectric effect, whenever you are getting the term photocurrent, so whenever you are getting all these things, immediately you have to get information into our mind, okay? Then only you can solve the problem, right? So that's what we will feel sometimes difficult in physics problems, okay? So why I am saying here means, you please understand. Now see, in this problem actually this photoelectric effect and stopping potential again I explained. So why I explained means, you have to keep in mind conceptually what is photoelectric effect and what is stopping potential, okay, right? See here, in an experiment of photoelectric effect, the stopping potential was measured to be V1 and V2 volts with the incident light of wavelength lambda and lambda by 2 respectively. The relation between V1 and V2 may be, so he is asking to find the relation between, right, V1 and V2, okay? See here, according to Einstein's photoelectric equation, H nu is equal to Ke maximum plus phi naught, okay? See here, Ke maximum is equal to H nu minus phi naught, Ke maximum is equal to H nu minus phi naught, okay, right? And you know that Ke maximum is equal to E V naught. I already told you, V naught and Vs both we are using to represent stopping potential, okay? See here, EVS is equal to, you know, in place of nu I can write C by lambda, no? So EVS is equal to HC by lambda minus phi naught, right? From this I can write Vs as a subject. Vs is equal to HC by lambda E minus phi naught by E, okay? This is what the equation or expression for stopping potential in terms of Planck's constant, speed of light, wavelength of the incident light, and charge of electron or E value. Here also the same thing, and phi naught is the work function. Okay, so this is the important thing while solving physics problems, right? So we have to write the same expression in our own words. That is what we need to solve the problem. Here he is asking to find the relation between two different stopping potential, otherwise two different cases the stopping potential. That's why we have to write the same expression whatever we have in terms of Vs as a subject. So Vs is equal to hc by lambda E minus phi naught by E. Next, according to the given problem, this is what V1 is equal to hc by lambda E minus phi naught by E. Their wavelength is lambda. But in case of V2, that is what hc by lambda by 2. It is what lambda by 2 into E minus phi naught by E. That is equation 2. Okay, right. And from these two things, V2 is this one, no, 2 hc by lambda E minus phi naught by E. That is equal to 2 hc by lambda E. Shall I write like this mathematically? Just I am adding and subtracting same quantity, that is what minus 2, that is what 2 phi naught by E. Then there is no change in the value of the equation, original equation. Okay, right. See here, 2 hc by lambda E minus 2 phi naught by E plus 2 phi naught by E minus phi naught by E as it is. Right. Now I am taking 2 as outside, so not for whole the equation, only from here to there. See here, 2 into hc by lambda E minus phi naught by E plus, it is plus 2 phi naught by E, it is minus phi naught by E. So I will write phi naught by E, I can write phi naught by E, that's it. So which is 2 into hc by lambda E minus phi naught by E plus phi naught by, right, as it is. Okay, this bracket also important, right? Okay, so V2 is equal, this one like to V1, it is V1, see here. So using equation 1, V2 is equal to 2V1 plus phi naught, right? So from this I can write V2 is greater than 2V1. V2 is greater than 2, because if you add something to the 2V1, then it will be equal to V2. So mathematically we can judge V2 is greater than 2V1. V2 is greater than 2V1. Okay, right. Next problem, that is 17th one. The maximum kinetic energy of emitted electrons in a photoelectric effect does not depend upon, the maximum kinetic energy of emitted electrons in a photoelectric effect does not depend upon. Okay, so it is actually they have given options, very well, 4 options are there. So here the options will be intensity, work function, wavelength, frequency. So the options are intensity, work function, wavelength and frequency. Okay, but out of these 4 options, whatever they have given, like intensity, work function, wavelength and frequency, you have to answer intensity. Okay, because the maximum kinetic energy of emitted electrons in a photoelectric effect does not depend upon intensity. Okay, that is important. Okay, right. Next, see here, next one, 18th one afterwards. Okay, the time taken by a photoelectron to come out after the photon strikes is approximately, okay, the time taken by a photoelectron to come out after the photon strikes is approximately. Okay, very well, when a metallic surface is there, right? So when invisible form of energy, okay, a form of energy, that is what light is going to incident on a metallic surface, that is what in the form of photons, right, is going to incident, then this photon's energy is going to absorb by the electron, and then electron will try to come out from the metallic surface. When the electron is trying to come out from the metallic surface, already positive charges are there. Okay, inside the metallic surface, not only electrons, positive charges also present. These positive charges will try to pull back the electron. Okay. And if the energy is sufficient for the electron to overcome this attraction, then it will come out. The minimum amount of energy for the electron to come out from the metallic surface is called as work function, right? So from the energy of the incident radiation, how much is there? Certain amount of energy utilized by the electron just to overcome the bond, just to overcome the attraction force by the positive charges, right? So the rest of the energy will convert in the form of kinetic energy of the electron. That's why we are calling it as maximum kinetic energy, because according to the law of conservation of energy, only three things are there. One is the energy of the incident radiation, and another one is the energy needed for the electron just to overcome the bond, to overcome the attraction by the positive charges. Okay, rest of the energy is going to convert in the form of kinetic energy of the electron, right? So that Einstein's photoelectric equation, we know E is equal to phi naught plus Ke maximum, phi naught plus Ke maximum. Okay, and here itself I already told you phi naught and W naught both we are using to represent work function. Okay, right. And here the question is the time taken by a photoelectron to come out after the photon strikes is approximately, right? There is a metallic surface, light is going to incident which is in the form of photons, right? Here he is asking the time taken by the electron, time taken by the photoelectron to come out after the photon strikes a metallic surface, right? When suppose when there is no striking means no photoelectric effect. Okay, when the photon is going to strike the metallic surface, after that it takes 10 to the power of minus 10 seconds. It takes 10 to the power of minus 10 seconds to come out from the metallic surface. Okay, so you can say that emission of photoelectron starts from the surface, incidence of photons, emission of photoelectron starts from the surface after incidence of photons is about 10 to the power of minus 10 seconds. Okay, right. Next, see here, next question, 19th question. The work function of a surface of a photosensitive material is 6.2 electron volt, right? The wavelength of the incident radiation for which the stopping potential is 5 volt lies in the so which region, UV region, infrared region, right, and visible region, right? So these are all different types of so the region means it represents the that is what range of wavelength, okay, right. So they have given work function. The work function of a surface of a photosensitive material is 6.2 electron volt. The wavelength of the incident radiation for which the stopping potential is 5 volts lies in the, okay, right. So you have to read the question, you have to understand the question, then we have to write the given things, that is what phi naught is equal to 6.2 electron volt, K maximum is equal to 5 electron volt, right. So phi naught is equal to, here what is phi naught is equal to, here that is 6.2 electron volt, and K maximum is equal to 5 electron volt, right, 5 electron volt. See here, observe carefully, see here so he is saying that work function, okay, right, and for which the stopping potential is 5 volts, okay, right. And if you observe carefully, this is what phi naught is equal to 6.2 electron volt and K maximum is equal to 5 electron volt. Then you can say that h nu is equal to 11.2 electron volt. No, h nu is equal to 11.2 electron volt. After that, you know, E is equal to E. This h nu means what? No? Which is what h nu? H nu is nothing but E only. No, E is equal to h nu, right? So this is what E value, that is 11.2 electron volt. Okay, 11.2 electron volt. So when it is 11.2 electron volt, so during from that addition, that is what E is equal to 5 naught plus Ke maximum, 5 naught plus Ke maximum. Okay, right. See here, so which is, you know, here which is 5 electron volt, and then we have to substitute these values here, that is lambda is equal to hc by E, 12,400 electron volt angstrom unit. Here 11.2 electron volt, these two will get cancelled, then the answer will be 1107. So 1107 angstrom unit, right? So based on this value you can decide the wavelength is in the ultraviolet region. The wavelength is in the ultraviolet region. Okay, right. Next problem, 20th one. A particle of mass 1 milligram has the same wavelength as an electron moving with a velocity of 3 into 10 to the power of 6 meter per second. 3 into 10 to the power of 6 meter per second. Okay. Afterwards, he is asking the velocity of the particle is. The velocity of the particle is, right? And mass of electron also given, that is 9.1 into 10 to the power of minus 31 kg. That is the mass of the electron. Okay. A particle of mass 1 milligram has the same wavelength as an electron moving with a velocity of 3 into 10 to the power of 6 meter per second. The velocity of the particle is. Okay. So this formula, you know, that is what de Broglie wavelength, like right, anyhow lambda is equal to h by p or h by mv, and you know lambda is same, he is saying according to the given information lambda is same. When lambda is same for two particles, then you can write like this, no, mp into vp is equal to me into ve, right? So h is already constant. According to the problem, lambda is constant, then mv is equal to constant, then you can write it as mp into vp is equal to me into ve. Now you start to substitute the values. Then here it will be 10 to the power of minus 6 into vp, 10 to the power of minus 6 into vp is equal to, this is what, 9.1 into 10 to the power of minus 31, 9.1 into 10 to the power of minus 31 into 3 into 10 to the power of 6, 3 into 10 to the power of 6. Okay. Now he is asking to find velocity of the particle, whatever it may be, right? Velocity of the particle, that will be here, you know, it is 9.1 into 10 to the power of minus 31 into 3 into 10 to the power of 6, right? It is 10 to the power of minus 6, no? So finally we will get it as 2.73 into 10 to the power of minus 18, 2.73 into 10 to the power of minus 18. Okay. And the mass of the particle they have given 1 milligram. This you have to convert into kilogram, because here we are taking in meter per second, no. This is also we are taking in kilogram, no. That's why this value we have to convert into kilogram. So 1 milligram if you convert into kilogram, it will be 10 to the power of minus 6. Okay. And then by substituting the values, we will get it as the velocity of the particle is 2.73 into 10 to the power of minus 18 meter per second. Next problem, 21. The figure shows a plot of photocurrent versus anode potential for a photosensitive surface for 3 different radiations. Okay, right. It is the model of, like, you know, they have given one graph, and by studying the graph, what is happening there, that we have to say, right? So this problem is in that model, right? I am not writing all the options. Just by seeing the picture, I can tell you what's happening there. Okay, see here, see these two things, right? And it is what anode potential, and it is what retarding potential, and this is photocurrent, and there are three things, that is what three different radiations, no? So A, B and C. Okay, by seeing this, I can say that curves A and B represents incident radiation of same frequency, but different intensities. Incident A and B represents incident radiations of same frequency, but different intensities. See here, different, because you have to understand that there is a relation between intensity and photocurrent. There is a relation between frequency and stopping potential. That is the point he is trying to catch from you, right? So by keeping those 2 points, you can answer to this graph. So answer to this graph means, first we are going to study the graph. After completion of that, we are going to answer based on the information what we have and what he is expecting from us. Okay, right. Next, see here, after completion of this, we have to go for, right, see here, that is what, okay, right, see here, sorry for this here, this part didn't cover just now. I will tell you once again, just within a matter of 2 minutes. Okay, see this. This is what first we completed up to here, no? For problem number 20, it is lambda is equal to h by mv, and here from this, when lambda is constant and h is constant, you can write mp into vp is equal to me into ve. That is equal to mass of this particle. They have given 10 to the power of 1 milligram given. If you convert into kgs, it is 10 to the power of minus 6 kg into vp. That is equal to, this side we have to substitute, that is what mass of electron and that is velocity of electron. Then by writing vp as a subject, right, so that you can find it is as a velocity of particle, and taking this 10 to the power of minus 6 to this side and doing this calculation, it will be 2.73 into 10 to the power of minus 8 meter per second. Right, next problem. Here the figure shows a plot of photocurrent versus anode potential for a photosensitive surface for 3 different radiations. Okay, see here. So this is the graph. Based on this graph, we have to answer, and there is a relation between frequency and stopping potential. That is what the retarding potential, and there is a relation between intensity and photocurrent. So that by seeing this graph and these 3, that is what these 3 different radiations A, B and C, you can say that the curves A and B represent incident radiations of same frequency, but of different intensities, Okay, right. So next problem, 22nd. See here, monochromatic light of wavelength 667 nanometers. Monochromatic light of wavelength 667 nanometers is produced by a helium neon laser. Full stop. The power emitted is 9 milliwatts. Okay, full stop. The number of photons arriving per second on the average at a target irradiated by this beam is, right. So here finally they have given wavelength and they have given power, asking to find number of photons. Okay, right. The formula for number of photons incident per second is equal to P by E. So power by energy, right. So power already given 9 milliwatts. So we are writing 9 into 10 to the power of minus 3 watts, because watt is the SI unit, divided by energy means, here you just concentrate energy means, that is what hc by lambda, no, hc, okay, h nu or hc by lambda. So that hc we are writing like this, hc we are writing 12,400 into 1.6 into 10 to the power of minus 19 angstrom unit. And Kila here, see this, that is already they have given 66, 67 nanometers. If you convert into meters, right, if you convert into angstrom unit, if you convert into angstrom unit, it is 6670 angstrom unit, okay. And here also angstrom unit, here also angstrom unit will get cancelled. And finally, if you do this mathematical process, we will get it as 3 into 10 to the power of 16. 3 into 10 to the power of 16 number of photons incident per second. Okay, right. So in this class we completed the problems from 15 to 22. In our next class we start with 23rd problem. Okay, right. Thank you.